Today we'll be doing assignments on the algebraic geometric problems what our wait a minute. So yeah, today we'll be presenting we'll be doing some problems on the previous class. So this is week 3 and the in the last class your professor Dilip Patil did problems on affine algebraic sets. Zariski topology and some examples. So today we'll be doing first and some exercises based on these 3 examples, and sorry. So first one will be for each of the following x y to find a set of polynomial s k x y such that x equals to Vs. So first one will be x equals to 0, 0, 0, 1, 1, 0, and 1, 1. Then second will be 0, 0, 1, 1. Third will be x-axis union 0, 1, and fourth will be describe the algebraic set V x y y z and z x of A3 geometrically. So take 5 minutes and try to answer this, then I will get back to you. And let me know if you have any problem so that we can discuss this. So the if you look at the graph and see the points, this is your 0 0, this is your 0 1, this is your 1 0, and this is your 1 1. So kind of this is a finite set, right, in A2. So one can see that it may have the I mean the set of polynomials, it may have more than one polynomial, because in this is a polynomial in two variable. So a polynomial in two variable may have more than usually have infinite solutions. So if you take like two irreducible polynomial, so they can meet like at finite points unless they are non-parallel or non-identical. So yeah, the first, so if you take like f1xy to x minus 1 and f2xy as y into y minus 1, then one can see that Vf1 intersection Vf2 is so exactly these 4 points, 0 1 1 1 1 0 0 0. How? Because you see v of f1 equals to should be 1 comma y and 0 comma y, where your y is arbitrary, right? And for v of f2 the solution should be x comma 0 and x comma 1, where your x is arbitrary. So when you intersect them you will get your answer. Now if you do the second one, so here where your x is 0 0 and 1 1, then again if you take g1 equals to x dot y minus 1 and g2 equals to y dot x minus 1, then v of g1 would be the x0 y and 1 comma x, sorry, or x comma 1. In both of the cases x and y are coming from k. And for vg2 one can see it can be x comma 0 and 1 comma y, where in both of the cases are coming from k. So v of g1 intersection v of g2 sorry should be only 0 comma 0 and 1 comma 1. So now for the third case, where your x is x-axis union 0 comma 1, which is a singleton set, then take h1 comma xy equals to xy and h2 comma xy should be y dot y minus 1, then v of h1 should be either x comma 0 or 0 comma y, xy coming from k, and v of h2 should be x comma 0 and x comma 1, so it should be x to k. Now if you again intersect them, v of h1 intersection v of h2, you will see it will be x comma 0 union 0 comma 1, right, which is nothing but your x-axis union 0 comma 1. So, and the fourth problem, if you see, that is this: describe the algebraic set x, y, y, z, z, x geometrically. So v of x, y, y, z, z, x to f3. So it means what? V of x, y intersection v of y, z intersection v of z, x, right? Then you will see that this means only that either x comma 0 or 0 comma y intersection, oh sorry, it should be 0 comma y comma z, x comma 0 comma z, intersection x comma 0 comma z, 0 comma sorry x comma y comma 0, intersection x comma 0 comma z, oh no 0 comma y comma z or x comma y comma 0. So what will be the possible solution? If you see that the points are only 3 axes, that is x axis, union y axis and z axis. You can see this, right? First coordinate, if you choose 0, here x should be 0 and here should be 0. Again from that y, from the second coordinate it should be 0. So yeah, one can see that I mean choose this, take x equals to 0 and this is 0, y 0 y. So here it is 0, so y you take should be 0, here you take should be 0, so you are getting that 0 0 1 0 0 z, right? That is your z axis. So similarly one can go through this and find others also. Now if we now we'll go to the second problem, that is one can see that or maybe we can start from Hilbert Null's challenges little bit, then we'll be doing some problems. Excuse me. So now okay, we will first start with the definition. An ideal I in a ring R is proper if I not equals to R. So maybe yeah. So an ideal I engineering is proper if I not equals to R. So we'll introduce a theorem. Actually, you have seen this Hilbert, Nals, Stellen, Sarts. For any algebraically closed field K, one, let I be any proper ideal in K x1 up to xn, then phi of I not equals to phi, and for 2 let I be any ideal. Notice that I haven't written proper or anything in K x1 up to xn, then I v of I equals to root I. This is radical of I which you have seen in the class. Now I will be skipping this proof for now because your professor may do this proof extensively in your next class, but we will be using this theorem to prove some beautiful results that I will be stating now. For suppose a theorem, say theorem for any algebraically closed field K, 1, assume I is a radical ideal in K x1 up to xn, and X is an algebraic set in An, then X is equals to Vi if and only if I is equals to I of X. And for the second, assume I1 and I2 are radical ideals in K of x1 up to xn. x1 is equals to v of I1 and x2 is equals to v of I2. Then I1 is contained in I2, respectively strictly contained if and only if x1 is contained in x2, respectively x1 strictly containing x2. So for proof of this theorem, now for the direct uh, okay, we will first prove one, that is assume that I is a radical ideal and in k x1 up to xn, and x is an algebraic set in an, then x equals to vi if and only if I is equals to I of x. Now the forward direction, we prove that by Nahl-Stellenger's we have I of x is equal to I of vi to root of I to I. Since I is a radical ideal, right? That is why we put root I equals to I, and this thing we are getting for Nahl-Stellenger's. So I is a radical ideal. Now the reverse direction, we prove like this. The algebraic set x can be written as x equals to vj for some j contained in x1 up to xn. Again, by Nahl-Stellenger's I will denote H and T for Hilbert Nahl-Stellenger's theorem. By H and T, V of I is V of Ix, which is nothing but V of I, V of j. So that is V of j radical. Since radical of an ideal contains the ideal, that means since j is contained in radical of j, we have V of I should be V of root j, which is containing V of j, where nothing but x. So it remains to show that x is contained in V of I. Now for every point P of x by the definition of V, we need to show that f of p equals to 0 for every f of I. But this is trivial, right? Since I equals to I of x. So we are done for the first proof. Now for the second proof, which is saying that Assume I1 and I2 are radical ideals in this polynomial ring, and x1 equals to vi1 and x2 equals to v of I2. Then I1 content containing I2 if and only if this. So try for 5 minutes, then I will be if you cannot do this, then I will be explaining this. Excuse me. So we'll be doing problem 2. Disappointed that I'm not getting response from any of you. Okay, the equivalence I1 containing I2 x1 to follows from the fact that I1 containing I2 VI2 VI1 and from here IV1 containing IP I2. So and V of I1 in VI2. This implies IV1 IV I2 is nothing but radical of I1 radical of I2 and I1 of I2 since they are radical ideals. So yeah, and the converse part one can try for themselves. Now we all know what is a prime ideal and what is a maximal ideal, and we also know that if I is a prime ideal, then R by I is integral domain, and if I is maximal, then R by I is a field. Now we'll be doing we'll be introducing another notion of a topological space, what is called irreducible topological space. So definition: an algebraic set X A in is irreducible if there does not exist a decomposition of X as a union of two strictly smaller algebraic sets. That means that if where x1 and x2 are closed in X, then either x1 is trivial or x2 is trivial. Or you can say equivalently x2 is x or x1 is x. Now an irreducible algebraic set irreducible algebraic set is also called an affine algebraic variety. So actually later part you will see that a variety means many more things about these algebraic sets, but for now I think irreducible is fine for classical geometry, but in scheme theoretic geometry a variety means it should be irreducible, reduced, finite type. But in affine case I think all these things are there, because there is a one correspondence between affine variety and finite type K algebra, because any affine variety is contained in a affine space, and so the corresponding rings should be finite type K algebra. So now first look at some example. We look at some examples in A2. That means affine plane. First, the algebraic set Vxy of A2 is the union of two coordinate axes. That is V of xy, it should be V of x and V of y, because product of two ideals, that means you can, I mean if you take variety of product of two ideals you can decompose them in as the union of two ideals. Since like x-axis can be written as V of y, right, and y-axis can be written as V of x, and they are not equal to V of xy, right, and also they are closed, so Vxy is reducible. Now look at the second example. The algebraic set V of x comma y in A2 consists of 0 0 only, right, that is it is singleton, so it cannot be decomposed as the union of two smaller algebraic sets. So V of x comma y is irreducible. Similarly, one can generalize this point is always irreducible. Now we'll first get our non-trivial result. We have seen the correspondence between radical ideal and algebraic sets, that is coming from Null-Stallingers, but we'll be seeing correspondence between prime ideal and irreducible affine algebraic sets, and which is very crucial for the next path of this course. So proposition: let I be a radical ideal R spec, that means radical ideal R spec is radical ideals, and x equals to v of I, the algebraic set in AN defined by I, then I is prime if and only if x is irreducible. Is prime if and only, yeah, I is prime if and only if x is irreducible. Now actually we will prove this by the contrapositive statement. We will prove this by the contrapositive statement. That is, x is reducible only if I is not prime. So yeah, this is the negation of the statement we have given earlier. So one can see that we can recover the previous statement from this. We first prove the forward direction, that is, when you take x is reducible, then your ideal is not prime. Now let x equals to x1 union x2 with algebraic sets x1 x2 which are not equals to x. Then x1, this implies I of x1, I of x, right? Because I is your radical ideal, so you can recover this. Hence there exists f1 which belongs to I of x1 minus I of x Similarly, x2 is contained in x implies that there exists f2 belongs to I of x2 minus I of x, right? Now the product f1 dot f2 vanishes at all points of x, right? Because f1 belongs to ix1, that is 0 for all points in x1, and f2 is 0 for all points in x2, and x is union of x1 and x2, so f1 dot f2 is 0 for all points of x. So f1 dot f2 belongs to I of x, but neither f1 nor f2 belongs to ix, so ix is not prime. This is a nice proof. For the second we again prove the negation. See, let I is not a prime ideal. Then there exists f1 f2 which does not belongs to I. Apply f1 f2 belongs to I. Now consider the set s1 equals to I union f1. Then x1 equals to v of s1 is an algebraic set, and since I is in s1, so x1 is in v of I, which is nothing but your x. And similarly, for x2 and s2 of I union f2, we have x2 is contained in x. we need to show that x1 union x2 equals to x. So one thing is trivial, right? That is x1 union x2 contained in x is trivial. Conversely, for any p belongs to x, I have f equals to 0 for every f of I moreover f1p dot f2p equals to 0, which implies either f1p equals to 0 or f2p equals to 0. Therefore, p of vs1 equals to x1 or p belongs to vs2 equals to x2. So this implies x is contained in x1 union x2. So we are done. So there is another theorem, but we are going theorem. But this is important. Let I be a radical ideal in kx1 up to xn, and x equals to vi, then I is maximal if and only if x is a point. I will do it. I will be doing this proof, but take first 5 minutes to think about it. Then I will be doing this. And again we will be doing this by contrapositive statement. That is, x is not a point. We prove the contrapositive that x is not a point, I is not maximal. So we first prove the forward direction. If x is not a point, then either x equals to empty set or x contains more than a point. Now if x is empty, then ix equals to your k action. But then sorry, my mic was turned off. So what we did was we proved the contrapositive thing, and that is, if x is not a point, I is not maximal. So first we do the forward direction, that is, if x is not a point, then either x equals to phi or x contains more than a point. So if x equals to phi, then I x equals to k x1 up to xn, then I of x then I of x is not a proper ideal. So not a maximal ideal. Now if x contains more than a point, then we can pick a subset y of x containing only one point, hence we have phi y x. Then we have k x1 up to xn I of empty set strictly containing I of y strictly containing I of x. Excuse me. Hence ix is not maximal because it is contained in a proper set, and any proper set is or proper ideal, any proper ideal is contained in a maximal ideal, so this is not a maximal ideal. Now we prove the prove the converse part. If I is not maximal, then either I is not a proper ideal or there exists an ideal. J such that I J K x1 to xn if I is not proper, then I is equal to k x1 up to xn. Hence x is equal to vi to phi, which is not a point. If I contains j k x1 up to xn for some ideal j, then we claim that we actually have I j k son of 2xn. Indeed, because we have I not containing j, but this may be containment or not. So moreover, by null Stellen search we have v of j not equals to phi, hence radical of j equals to I of v of j not containing k of x1 up to xn. With this claim, we see that v v of I, v of root j is phi. It follows that v of root j contains at least one point, hence x of vi contains more than one point. So we are done, right? So what we have shown till now, that this is that I maximal if and only if x is a point, I is prime if and only if x is irreducible, and in your last class you have seen that I is radical if and only if x is algebraic set. So we can really give a nice correspondence, that is bijection. So actually let's do this no in a fresh page. Radical ideals in k x1 up to xn, which corresponds with algebraic sets in an in p and I correspondence. Now this contains prime ideals which again corresponds with irreducible algebraic sets in an, which again contains maximal ideals and which corresponds with actually it would be better if you just say closed points. And n. Now we'll do an exercise which is called a twisted cubic. It's actually good exercise. I will give you, like, this is little big, so I'll give you 5 to 6 minutes to give me at least an intuition, so that it can be better for all of us. The twisted cubic. To prove this, it's a famous example. So prove that the subset in A3 given by x equals to t square t cube belongs to A3, t belongs to k is an affine variety okay. So let's try for 6 to 7 minutes. We'll be meeting again at 7:35. Okay. So we'll be doing this proof, and this will be our last proof today. So we first show that x belongs to vi for some I of k x y z. Now for every point t square t cube of x, we have y minus x square equals to t square minus t square equals to 0, and z minus x cube equals to 0. As okay, we'll break it down. Z should be t cube minus t cube, so it should be 0. So hence if I take I to be y minus x square and z minus x cube, one sees that x belongs to v of I. Now consider the ring homomorphism phi of k x y z to kt such that phi of x y z going to f of t square t cube. Now in the last tutorial session, by the fundamental, so this is surjective map, right? You can take just any polynomial in fx and you will recover all the polynomials from ft. So this is a surjective map. By the fundamental isomorphism theorem, we have image of phi is isomorphic to kxyz by car phi. Since phi is surjective, we have we have image of phi equals to kt. Now to find out car phi, we claim that every fxyz from kxyz can be written in the form if y minus x square g1 and z minus x cube g2 plus h. Where g1 comma g2 belongs to k of x y comma z and h belongs to kx. To see this, think of f as a polynomial in y and consider the Euclidean division of f by y minus x square. There is a quotient g1 and a remainder r1 of kx, right? Then again think of r1 as a polynomial in z and consider the Euclidean division of r1 by z minus x cube. There is a quotient g2 kxyz and a remainder h of kx. So putting in formulas, f equals to y minus x square to g1 plus r1, y minus x square into g1 plus z minus x cube to g2 plus h. So now we find the image of f under phi is given by phi of f t square minus t square phi of g1 plus t cube minus t cube phi of g2 plus phi of h. Now these are all 0, 0 plus 0, and as phi of h is h of t, so therefore phi of f 0 is equivalent to h equals to 0, f equals to y minus x square okay 0, and this is equivalent to y minus x square g1 z minus x cube g2. This is equivalent to y minus x square z minus x cube. So this means a car of phi equals to y minus x square z minus x cube equals to I. So kt is isomorphic to kxyz by I. Now since kt is an integral domain, kt is an integral domain, by proposition we conclude that I is a prime ideal. Hence a radical ideal. So that means x equals to phi implies I equals to I of x. Since I is a prime ideal, x is an affine variety. So what we have done is that to prove that x is an affine variety, and also in this condition, if your xyz belongs to phi of I, then you see that y is equal to x square and z equals to x cube. So x square x cube, it is of this format, which belongs to x, right, which is of the form t square t cube. So your x equals to phi. Now I think we are done. And also polynomial ring of a Euclidean domain So what we have done is that the main trick is to dissect this polynomial into these parts so that we can actually have this formation, and we can do it accordingly here. So I hope you enjoyed this lecture, and I really suggest to carefully follow Dr. Patil's lectures, because he's giving exceptional good lectures. And to do some exercise from Atia MacDonald or David Eisenbart, competitive algebra with view towards algebraic geometry. Okay, so we will be meeting on next Tuesday. and when you will be viewing this lecture in YouTube, if you have any doubt, try to contact me in my email. My email address is this. Okay. Okay, so thank you everyone.